Hey everybody. Alright, so today we're going to be talking about the end of the age of dinosaurs. So I'll be talking about the extinction that purportedly killed off many of the dinosaur groups that we know and love. And then we'll be talking about the beginning of the Cenozoic. Alright, so here's a picture, or a graph, depicting all of the mass extinctions through time. Alright, so you'll notice here that the black bar, which is indicating the amount of extinction at the bottom here, is never at zero, meaning extinctions are always happening during all periods of time. Alright, so I know we only talk about extinctions happening, at certain points, like the end of the Permian, or today, like the end of the Cretaceous, but extinction is always a constant. Alright, so again, here are the big five mass extinctions: the end Ordovician, Devonian, Permian, Triassic, which is one we didn't really talk about, but it did happen. And then finally, the one today, the end Cretaceous. And as you can see, the end Cretaceous was kind of a doozy, all right? A lot of stuff went extinct. And the ones that we're going to be focusing on are, of course, the non-avian dinosaurs, meaning the dinosaurs that don't belong to the birds. Remember that all birds are dinosaurs, but not all dinosaurs are birds, if that makes sense, all right? So let's talk about this. Now, there's some evidence to suggest that many dinosaur groups, like the sauropods, the longnecks, were actually already declining by the time the extinction happened. But we're not going to talk about that too much because we're not really sure what's going on yet. All right, so what happened? All right, so there's been a number of different ideas as to what happened for dinosaur extinction. So some of them have included an asteroid impact, aliens, yes, really, solar radiation poisoning, mass blindness in dinosaurs. All kinds of shenanigans have been proposed. So we're going to be talking about the ones that have been most supported by science in the past couple decades. All right, so the KPG extinction. This is also sometimes referred to as the KT extinction. Doesn't really matter. All right, so this extinction was global, and it affected both marine and terrestrial organisms. And for an example here of a marine organism that was killed, here's the ammonite. It's closely related to octopuses today, and it was an absolutely fierce hunter. Some of them got up to larger than human sizes. Seriously, Google ammonites from Texas. It's horrifying. So, up until the 1980s, scientists thought that this was related completely to fairly normal climate change, meaning it got a little hotter on Earth during the Cretaceous, and maybe that's what essentially killed them. So, that's about to change with this next slide here. So, here we have Walter and Walter Alvarez. All right, you may have figured out the name is not a coincidence. They are father and son. They did a lot of their field work together. So they were really interested in what happened to the non-avian dinosaurs. And so they went looking to see what they could find. And what they found was this layer in a rock indicated by that arrow on the right side image right there. And I know what you're thinking, right? How did anybody miss that? It's very blatant, isn't it? Well, no, of course not. I'm joking. But what it is it's a layer of iridium. And you may not know what iridium is, and that's okay. But the clue is it has an atomic number of 77. So where is it formed? If you'll remember with me, back in the first part of the class, we talked about elements heavier than iron, and they have to be formed in a very specific way. Meaning, we don't have iron formation happening just spontaneously. We have to have it happening in a stellar explosion. All right? So, iridium is considered a rare earth element, meaning it's not commonly found on Earth because all of our iridium is found in the core, right? It's very dense, so we know what happens to Earth's layers today. They were density stratified, so the heaviest stuff sank to the core, the medium heavy stuff sank to the mantle, and the lightest stuff is on the crust, where we are. All right? So if it's on the crust, just like with iron, it must have come from a meteorite or an asteroid. All right? So look that up in the Origins of the Universe PowerPoint if you don't remember that and want a review. So, other evidence. So they found this layer of iridium, and they started looking for it all over the world, and lo and behold, they found it. And all of it was dated to 65 million years ago. All right, they found it in Denmark, they found it in North America, they found it in parts of Asia, all over the place. All right, so another line of evidence is what's called shocked quartz. All right, so shocked quartz is a really good piece of evidence for an asteroid impact. And the reason for that is quartz is a very common mineral. You'll see it a lot of the times in pebbles. It's the same thing. Amethyst is a type of quartz, that purple mineral. All right, so quartz is very common. And it's very hard, meaning it's very stable. It doesn't get destroyed easily. And what you're looking at, these images, is quartz that has been shocked, meaning it's been hit so hard, it's been completely rearranged. So it doesn't even look like quartz anymore, all right? And this can only happen when quartz goes under an immense amount of pressure but does not melt. And one of the only ways we can do this that we know of is an asteroid impact. So there's another line of evidence there. The third line, tektites. And tektite means a larger glass bead. And how these form is when rock is melted. All right, it's melted and it's blown into the air and it cools as like droplets in the air. All right, so it's forming as like little tiny glass beads. So we find all three of these lines of evidence, and all of these are starting to lead us to an asteroid impact of some kind. So where is it? Now, one of the easiest ways to start looking for this is see where the largest amount of shocked quartz and tektites are forming. All right, so let's take a look at that. As you can see, the debris field is concentrated towards North America. All right, so what this debris field is showing here is at the impact, right? So we know a little bit more about this now than we did in the past, but we noticed that there was a lot of debris in North America, all right? Specifically the southern portions of North America. So what we're gonna look at here is this T equals blank hours, all right? So it's time after the impact. So what we look at here is the spreading of the tektites and the shock quartz through time. And you can see that they're spreading their range. All right, and it's in a pretty predictable pattern. This is based on what we know now about where these shocked quartz and tektites have been found. All right, but there you go. You can see that video right there. We'll wait for it to finish playing again before we move over. All right, so the problem. We have these shocked quartz. We have tektites. We even have a map of where they may have been, showing us where that asteroid impact might be. We have a really thick layer of iridium, first discovered in Italy, if you're interested, and all of it's dated to about 65 million years ago using multiple different tests of radiometric dating. However, you would imagine that we would find an impact crater, right? That would make sense. We have all of this stuff leading us towards an impact, but there's no crater. So that's a problem. All right. So luckily, a couple years later, we did find it. But first, let's look at this really ridiculously dramatic image of pterosaurs trying to flee the asteroid impact. It's probably not based in reality, but it is pretty cool. All right. So the evidence. All right, so let's take a look at this map. This map looks like a strange blob filled with colors, right? All right. So this map doesn't really make a whole lot of sense to anybody. But if you take a look in the center, you see that blue concentration, right in the center of this map, and you see a little hole in it, and that hole indicates that something is very large, right? And what that means, let me rephrase that doesn't make sense. That very large hole there is showing that there's a giant depression. It's a gravitational anomaly. An anomaly means something that's unusual. So this is a map that a geophysicist produced of the ocean basins. All right, and one of the reasons we hadn't been able to find the ocean or the crater before was because it was underwater, and it's a lot harder to see things that are under the ocean. So let's not stop looking at this pretty confusing map here, and let's take a look at a diagram of it. So here it is. Most of it's underwater, so it's hard to see. This is called the Chicxulub crater. It's off the Yucatan Peninsula in Mexico. All right, and you can see it here. It's sitting in the Gulf of Mexico. All right, fairly close to Cuba. And it's about 100 miles wide and 40 miles deep. That's massive. All right. So what would have happened? An impact of this size would have been equivalent to about 5 billion times more powerful than a single nuclear bomb. So you can imagine that just this one asteroid impact had massive implications for life on Earth. So let's talk about what those effects may have been. And I'm sure you can think of some, but let's go through a couple examples. All right. So first, a mega tsunami. All right. So I know this picture is wildly dramatic, Probably also not based in reality, but again, it looks cool, so we'll forgive it. So a tsunami is essentially a giant amount of water movement being caused by some kind of seismic trip. All right. So a lot of tsunamis are caused by earthquakes. We have that motion and it sets off a massive wave. All right. So we've seen these in the news. There's many of them in the Ring of Fire, which is in the Pacific. And we have so many earthquakes there, of course, because it's convergent plate boundaries, which you guys know. But this one would have been triggered by an asteroid. And as you can imagine, this one would have made tsunamis incredibly high. So we're talking waves that would have completely engulfed skyscrapers, right? Now, the reason we know this happened is we actually have geological deposits of the remains of tsunamis. They leave very specific marks on beach rocks and on shores, and we have those preserved from about 65 million years ago. So we do know they happened. And let's take a look at this graph, all right? So what we have here in the x-axis is time in weeks after impact, all right? So we have 0 to 30 weeks. And on the y-axis, we have a gradational scale showing you what it would have looked like outside, essentially. Not really a numerical scale, but the amount of solar radiation getting through, so the amount of sunlight. And you guys all know that plants can't survive really without sunlight, right? They need to photosynthesize. So immediately after the impact, it was total darkness. Could plants photosynthesize? No, they couldn't. And they couldn't for months after the impact. That's a pretty big problem, right? We had a mass extinction of plants just about this time. And as you can imagine, we also had a mass extinction of herbivores. If you can imagine with me, long-necked dinosaurs are not going to do well without plant material. All right. So it took absolutely months for the ash from this asteroid impact to clear, right? So when this asteroid hit, it kicked up tons of dust and dirt and actually blocked out the sunlight, just like a volcano would. All right. So the tsunami and this are short-term effects of the mass extinction, or of the asteroid impact that caused the mass extinction. Short-term impacts. So other icky side effects. It rained acid rain. They had massive forest fires. You can actually see that in the rock record. Forest fires are marked by very specific chemicals. Everything within a certain range of the asteroid would have been vaporized. Literally just vaporized. So is this an example of natural selection? So if you'll remember, this is something that we talked about during the first part of the class too. Natural selection is essentially some things are better suited for an environment, and those things that are better suited reproduce more, and those genes are passed on. This is not an example of natural selection here, because nothing is reproducing and is slightly better capable of handling being vaporized. It's just killing everything in its path. So evolutionary trends don't necessarily have to be because of natural selection. We can also have things like mass extinctions by asteroids that can affect evolutionary trends too, just to get you thinking about it. All right, so this sounds like a pretty crappy day for the dinosaurs, right? Yeah. All right, but is this the whole story? Not necessarily. So let's add to this story, just to make this time even better on Earth. It's also possible that the asteroids triggered strong volcanism. Now, this isn't definitive. This may change. The science is still up for debate, all right? But we do know there were a number of volcanic impacts that went off about 65 million years ago too. So let's take a look at those. So here are the Deccan traps. And again, a trap is just the term for a lot of volcanic rock, right? Just like the Siberian traps and the Amican traps from the Permo-Triassic and the Devonian extinctions respectively. So here they are in India, and they cover a wide amount of India, don't they? Absolutely. Okay, so here's what they look like. They originally covered 800,000 square miles of rock, and these rocks are over a mile thick in some places. Now, these aren't facts I need you to know, but pay attention to the last one. They occurred within the span of less than 1 million years. That's really fast, all right? So this would have had catastrophic climate change effects, even if there wasn't an asteroid. So let's take a look at what may have happened. So there are some scientists that suspect that when the asteroid hit, and you can see in the top left corner, there's like a little push pin where the Chicxulub crater impact site is. All right. And when it hit, it triggered incredibly incredibly high seismic waves that traveled throughout the entire Earth. And that's what that lower left corner image is showing you, essentially how the shock waves and everything would have traveled. And you'll notice that some things do travel through the core and some things don't. If you're interested, we can talk about that more, but those are called P waves and S waves, and they travel through the Earth differently. This has to deal with earthquake science. You can come talk to me if you ever want to know more. But some scientists believe that the amount of seismic activity. To sum up, the short-term effects of the extinction would have been things like acid rain or the temporary cooling from the sun being blocked out, right, by all the ash the asteroid kicked up, the tsunamis, etc. The long-term effects are going to be things like the greenhouse gases that were emitted from the volcanoes that can cause intense warming and take millions of years to disappear. All right, so now we're going to talk about the Cenozoic. So you're crossing the boundary from the Mesozoic to the Cenozoic, and the KPG extinction is what separates those two. All right, so here we have a cartoon of the T-Rex interpretation of how the extinction went down. Very brave. All right, so the Cenozoic. We're finally into the most recent time. All right, we're into the Cenozoic era. This encompasses 65 million years ago to literally today. All right, so just think you've already made it through just about 4 some odd billion years of evolution in just the course of 3 months. Look at you go. All right, so into the Paleocene. All right, so let's look at the Paleocene again. Sorry, it's right there at the bottom in this orange color. All right, so today we're going to be talking about the Paleocene and the Eocene. So those two words right there, Paleocene, Eocene, just so you know where we are. So during this time, you can look at this world and you can say, yeah, this looks pretty familiar, right? So once Pangea breaks up, they're breaking apart into fairly familiar shapes. But of course you notice that, well, one, part of Africa is underwater, a giant chunk of Europe, a giant chunk of North America and South America, all of this is underwater, meaning there's not a lot of ice. So if we were to take an oxygen isotope record from this time, you would likely find an even mix of oxygen 16 and 18, right? Because there's no ice. Look at Antarctica. There's no ice there either. So obviously there's some differences in where things are. So let's take a look at some of these differences. One, North America and Asia are still connected, right? Europe and Greenland are still connected. Antarctica is still connected to South America and Australia. It's already broken apart from Africa, but Australia and South America, they're going to hold on for a little bit longer. All right. And one last thing to note, of course, is India. India is hanging out all by itself right now in the Indian Ocean, but it's zooming its way on up to Asia. So it will connect in the next couple million years with the rest of Asia, forming the Himalayan mountains. All right, so the after effects of the KT extinction. So I'm really sorry I forgot to change that to KPG. The name was recently changed from tertiary to Paleogene, so it means the exact same thing. Don't worry about it. All right, but it was cold from all that ash, followed by intense heat from the global greenhouse gases. After millions of years, it's going to settle down into fairly cool and dry conditions. All right, it will settle down. Here's just another very dramatic interpretation of that asteroid. However, we're moving in, so after quite a few million years, everything's calmed down from that extinction. We're going to see something very strange happen. The Paleocene-Eocene thermal maximum. Thermal means heat. Maximum means the most. So it's going to get really hot. And again, the Paleocene and Eocene are just time units. So smack at the Paleocene-Eocene boundary, which is how we define this boundary, is an intense rise in heat. So take a look at this graph here. All right. So focus only on the Paleocene-Eocene, which is the left-hand part of this. And we see the label PETM. And you notice with that line, it shoots straight up to about 5 to 8 degrees Celsius. So it got about 5 to 8 degrees Celsius warmer on average in a very short amount of time. All right. And that's about 10 degrees Fahrenheit. So that's a huge change. How do we know this happened? What evidence do we have to support this idea? Well, we have a lot of evidence. So let's take a look at the isotope record, everybody's favorite. All right. So first we have the carbon-13 graphs. All right. That's the topmost graph right there. Remember, we only have 13 because plants break down 12. So we only see the 13 in the rock record. And if you remember, carbon-13 tracks photosynthesis. The more carbon-13 we have, the more photosynthesis we have. The less carbon-13 we have, the less photosynthesis. All right. So we know that when we have more photosynthesis, it's usually cooler outside. Like today, we're trying to plant trees. to cool it down outside. So if we have a drop in photosynthesis, it's probably going to be pretty warm. So take a look at this graph here. Do you see the gigantic decrease in carbon-13? It's exactly at the boundary of the Paleocene-Eocene thermal maximum, which I'm going to call the PETM from now on. All right? Now let's take a look at the second one, oxygen-18. Oxygen-18 and oxygen-16 are the two isotopes we're concerned about. 16 is what makes up ice. So if we have ice, it's completely oxygen-16. So in times of really cold weather, we only find oxygen-18 preserved because that 16 is in the ice. So if it's warm outside, we should see a decrease in 18. And do we? Well, let's take a look. Now, first note that the axis on this oxygen-18 graph, it's backwards from what you're used to. So the negative numbers are actually going up. So we do see a decrease, and that correlates with an increase in temperature. So look at the right-hand y-axis. You see that temperature graph is going straight up. So there's two lines of evidence. We have less C13, and we have a decrease in 18 with respect to 16. Now, let's take a look at this third one. This one you're probably not as familiar with, but that's okay. So that's CaCO3. That's calcium carbonate, all right? And calcium carbonate, again, is what makes up coral and starfish and snails and clams. So if you remember, we've talked about times when it got really, really, really hot outside, all right? And it actually it made everything a lot more acidic, all right? And organisms that build their bodies out of CaCO3, calcium carbonate, their bodies actually have a harder time staying put in high acid. That's something that's going on now with coral bleaching, right? And ocean acidification. So during this time, we had the same problem. Look at that dip in the CaCO3 in a really short amount of time. So what we know is the oceans were a lot warmer, probably because of all the increased CO2, and CO2 makes the oceans more acidic, which means the amount of CaCO3, which is what organisms build their body out of, they're not going to do so well. All right, so let's take a look at what may have happened. So possible causes include volcanism, again, and methane hydrate release. So volcanism we're probably pretty familiar with, right? They shoot out lots of ash, which cools it down temporarily, but in the long term, it increases the amount of greenhouse gases. Methane hydrates, of course, we talked about those. Methane hydrates are powerfully dangerous in terms of global warming because they hold in so much more energy than just CO2. I hope you remember we talked about that because it will come up again. All right. So if we accidentally melt ice where that methane is being held, it can release it into the atmosphere. And if you'll remember, we're worried about that happening again today. All right. So that's why it's so dangerous. So what did this actually cause? All right. So first, we had a major faunal exchange. And what that means is animals that like warm weather now have all this new opportunity to expand their roots, get some new real estate. All right. So we have the spread of warm adapted animals into high latitudes. So crocodiles and things are making their way on up north. So clearly this is not a good scenario. I don't know about you, but I'm fine with crocodiles staying, where they are right now. And we had diversifications across many of these groups. For example, the snakes and lizards. You don't need to know the word lepidosaur. That's just a scientific name. Crocodilians. And birds. So take a look at this bird. This is much taller than me. It's about 6.5, 7 feet. This is called a terror bird. It may look cute, but as its name suggests, it's terrifying. Okay, so the PETM. Let's take a look at this. How much carbon was actually being put into the atmosphere? All right, so that's the blue line, which is the line marked PETM. All right, that's 2 billion tons of carbon per year. It did all this from 2 billion tons. So now let's take a look at what we're doing today. And I know you've seen this graph before, but this is a really important point, so I hope you pay attention. And so our current, the red line, is 30 billion tons of metric tons of carbon per year. So remember that even though, yes, climate has changed in the past and it's gotten much hotter, we're doing so at a rate that is absolutely unprecedented, meaning we can't possibly know just how severe these effects are going to be. So something that happened during the PETM, which is something we've already talked about, is thermohaline circulation being stopped. Now, thermohaline circulation, as a review, thermo means heat, haline means salt. The oceans are circulating based on differences in density of heat and salt. So cold water is denser, so it sinks. Salty water is denser, so it sinks. So the bottom of the ocean is filled with cold, salty water, and that motion of the sinking and the rising of the warm and cold water actually allows the oceans to circulate. All right, but if we warm the Earth up 5 to 8 degrees Celsius, it can actually stop thermohaline circulation, which will promote a lack of oxygen in the oceans, which, of course, as you know, is not good. All right, and again, you should know how this works. It's going to come up again. Hint on your exam. All right, so again, climate has changed throughout the entire history of Earth. This is not a reason to think that we shouldn't care about climate change now. So this should be an excellent warning that we already know what can happen with this level of climate change. So we have a great idea about what we can do to prevent these from happening. And this is one of the most important lessons that I really want you to get for this class. All right? Okay, so terrestrial diversity. During this time, we're going to see a diversity of mammalian groups forming. Cetaceans, which are whales and dolphins. Sirenians, like the manatees, something you should be familiar with in Florida. All right. And these are secondarily aquatic. So this trend to becoming secondarily aquatic starts in the Eocene. And whale evolution is a beautifully documented thing that we see in the fossil record. And this is what we call transitional fossils, meaning these fossils have evidence of land-dwelling creatures with their more marine ancestors. And we can see these transitions happening throughout geologic time. All right, so this is a page out of Pandas and People, which is that textbook I told you. It's an intelligent design textbook that rejects the theory of evolution by natural selection. And one of the reasons they reject it is because there are no clear transitional fossils linking land mammals to whales. And we're going to take a look at just a few of these transitional fossils, meaning that unfortunately, this is a refusal to accept the falsification of their hypotheses, right? Again, intelligent design is a speculation. All right, so let's take a look at some of these. So first off, almost all of these are found in a beautiful place called Pakistan, right? Where these fossils are just gorgeously preserved, all right? And there are many more transitional fossils and transitional species of these whales. These are just a few. So take a look here at this phylogenetic tree. And what you see here is a change through time, starting with Indohyus at the bottom and Balena up at the top, the modern whale. All right. And what you notice here, look at the tail. Do you see the tail changing from a more terrestrial-like tail to an aquatic tail? Take a look at the legs. Notice how they're getting smaller and smaller and even more flipper-like through time, like especially with Rhodocetus right there in the middle, more flipper-like. Take a look at the face. The face is changing shape to a more aquatic shape. And we can actually see all these transitions in the fossil record. It's beautiful. So here's the ancestor of whales, right here. It was an aquatic hunter, maybe like a bear today. Really graceful in the water, but it could also walk on land just fine. Its ears are structured in a way that it could likely hear underwater, kind of like how we can, not really well, but it can hear. And as you can imagine, hearing underwater if you're an aquatic hunter is going to be incredibly important. So if you have offspring that can hear a little bit better, those are the traits that are going to be selected for. So now let's ask a question that probably keeps you up at night. Can dolphins and whales smell? All right, so to paint the backstory here, fish have a very special type of smelling gene. All right, they can smell underwater just like sharks can too. Land animals can't, right? You and I, we cannot smell underwater. So land animals have changed their genes through time so that they can no longer smell underwater, but they can smell on land. So can dolphins and whales smell on water or land? An interesting question. The answer is they cannot smell underwater. They have land genes. So smelling genes in whales and dolphins are almost identical to the ones you and I have. They actually cannot smell underwater. All right, they have to surface. So let's take a look at another transition in whales. This is the blowhole. Take a look at the one from 50 million years ago up in the top left corner. Now take a look at the one 45 million years ago and 40 million years ago. And then finally, look at the one from 15 million years ago in the dolphins, Delphinidae. That's the dolphin family. All right. This keeps moving up and up and up the face, and we have this beautiful transition of it happening. In number one here, at 15 million years ago, that's very clearly a terrestrial animal, right? The rest of the skeleton says so too. But the skull is very clearly terrestrial, And by the time we get to 15 million years ago, so 35 million years of evolution passing, This thing is very clearly moved to an aquatic lifestyle. So just to sum up just a few of the transitions we see nostrils moving up towards the snout to the top of the head. The hind legs get smaller and smaller and smaller. Remember, modern whales still have those legs. And we see something called the fatty deposit in a jaw increasing. We call that the melon. So let's take a look at what I mean by that. So why would a fatty deposit in a jaw increase? All right, so let's take a look at this. Take a look at the top whale there. The head is expanded, and there's many reasons for that, but one of the ones we're going to look at is echolocation. So the two arrows here are actually indicating those fatty deposits called the melon, right? And how this is working is the whale is actually using echolocation to hear and to sense things, all right? So sound waves of some kind are moved into, or towards the whale, or the dolphin, all right? And they're processed through these fatty deposits, and they can actually make those noises back out, pass those sound waves through. So they're hearing in a way that's very different from you and I, but it's an incredibly effective mode of communication, all right? We actually see the transition of that increasing through whales through time. It's really cool, huh? Come talk to me if you ever want to know more. All right, so this is where we're going to stop, all right? So we're going to pick back up with this next week. Thank you for listening. All right, take the short quiz on this, and I will see you in a week. Have a good day.